Okay, I have two quick announcements in terms of logistics. Two announcements, one apology. I told you the wrong thing last week. I was looking at problems 26 and 27 that were supposed to be done after Tuesday class. And instead, I should have been focusing on problem 21, which was due before Thursday class. Not sure where that distinction comes from. But that actually 21 was the problem that I would like to discuss in class. No big deal. I will do it next Tuesday. We will keep talking about Jacobians for a while. But if you want to give that a shot until next Tuesday, that would be a good idea. I'm not sure if... How much did it confuse you? Not much. I was about to ask on a scale from 0 to 10, is it a solid 9.5? No, more 3? So 2-ish? Oh, I thought you talked about the fact that I announced the wrong problem. No, that was... OK, so we will talk about this next Tuesday. Then I haven't checked if Iskander uploaded the new solutions and pushed the new templates. Did anyone check? He normally does this on Thursdays, but he called in sick today, so I'm not sure if it happened. Otherwise, I'm sure it will happen tomorrow. Any other questions on logistics? Then I want to dive right in, right? We are in this process of basically developing an algorithm to solve the forward kinematic problem, where forward kinematic problem is compute x from Q, where we haven't really defined what x means, and we haven't really defined what Q means, apart from sort of a loose definition through a bunch of examples. But this is where we will get to today. Can I ask you something? Because, I mean, I had to notice that you're coming late to almost every lecture. Is there a particular reason? Do you have another lecture before? OK, can we just stop that? Because every time someone comes late in a room that is nearly packed, it disturbs the entire class. OK, so today was simply last time that this happened. And what we did first, before diving basically into the details what x and q mean, we developed an algorithm, a recursive algorithm that exploits this linked tree, right? This linked tree structure in which we want to store the topology of a system. So what is connected to what, right? In this case, it's a little bit of a special linked list because we have two different types of objects. We have bodies and we have joints, right? And between two bodies, there is a joint. And because we have this tree structure, we also have to be a little bit careful that not every body necessarily has a child joint or a single child joint, right? Could be 0 if it's a leaf, could be multiple if the tree is branching, and not every body has a parent joint. The exception here is ground or the root of the tree. That's a little bit different to sort of a typical linked list where you have the same objects and they're always connected to each other. Or one object is connected to exactly one other object. And then we looked at two algorithms that I want to write down in a more formal way than basically the game that we played last lecture. And the two algorithms that we talked about were the inward pass and the outward pass. The inward pass, or all algorithms are basically relying on this interplay between bodies and joints. And they're always started somewhere from the outside, from a main routine. And this one starts with an arbitrary body. The examples that we used were always, we started with a leaf. But you can do this with any arbitrary body. where an arbitrary body or every body object somehow provides a method that allows you to inquire the position x of a body, right? In our silly example, that was simply the angle of this object because we only cared about rotations in 3D. And then within this body, the routine basically has to make a decision based on, is this body root or not? Right? And this is why we carry this flag, is root. And if the body is root, then the answer is simple, return 0. And this is basically where we make this assumption that our ground coordinate system, in a sense, right, we would say that the center of gravity of ground is by definition positioned at location 0, right? In 3D, this would be really 0, 0, 0, and has sort of an orientation given by the identity matrix. So this is our world coordinate system. That's why this always works. If a body all right, I'm sorry. This, if you overhear, this all looks black. No, it was black before, right? And now it turned orange? Or is this just my eyes?
It's orange.
Okay. Was it orange all the time? All right, I should check my eyes, because this should just look black. Maybe it's just a perspective. Right, so if the body is root, then it knows the answer. It can simply reply to this inquiry, hey, what's your orientation, what's your position, and the answer is 0. Right? If not, the body needs to get the position from where? Sorry? Which joint? No. The parent joint. Parent joint is the joint that connects you towards root. So you have to get the position from parent joint.
Is a get not a set?
No, it's a get, right? You want to know your position, and if you're root, you know the answer as a body. If you're not root, you have no clue. But the only one who can tell you is your parent joint, because that somehow connects you to ground. And then also importantly, that always works, right? If I'm root, I know the answer. If I'm not root, I per definition have a parent joint, and I can ask that parent joint. And then we ask the parent joint, which basically means that within a joint object, we have a corresponding method that is called somehow, I call it inquire x from a joint. And joints, they don't have a choice, right? For joints, there's always a predecessor, there's always a successor. They don't have to make a decision here based on any flags, because for joint, the situation is always the same. So the first thing they do is they acquire the x, the position and orientation of the predecessor body. And that basically means calling exactly this function that we wrote down in orange. Once they know the position of the predecessor body, they then can go ahead and essentially return the position of their successor body. And to do that, they have to do a little bit of math, right? They take the position of the predecessor body, some x, and add some delta x, which depends on q, where q is what is going on in this particular joint. So a rotational joint would add a little bit of rotation, translational joint would add a little bit of translation. What we mean with x and delta x and q, we will talk about in more detail later on. Now, on first glance, this looks like I'm doing an infinite loop, right? Body as joint, joint as body. How can this ever be resolved? But at every call, we talk to different bodies and joints, right? As the main program, I ask some leaf. The leaf asks its parent joint, and that parent joint asks its predecessor body. So the second time I arrive here at this orange code, I'm calling this function of a different object, of a body one step down in the hierarchy in this tree, and then that body calls the function of its parent joint, so again a different joint object, and so on and so forth. And that loop is bound to end at some point, because we know we have a kinematic tree. It's a directed graph which has no loops, which is fully connected, which means I will always have a unique connection to the root of that graph, which means at some point I will end up here. And I will then basically end the loop, right? Return 0 as the location of ground. And at that point, that's basically now when the information flows backwards, where ground informs one of its child joint, right? Whoever asked, I'm at location 0. That child joint can update the location of its successor. That successor can then answer the question or the inquiry of one of its child joints, and so on, until at some point a body can basically reply to the main routine. In the background, there is this idea of exploiting self-similarity through recursion. So what we will do here is we basically treat our kinematic tree as shorter and shorter sub-branches. Right? So when I call this function here, inquire x of a body, that body sits somewhere at the end of a branch. And branch, I mean a path between root and that body. And then by basically going through the cycle once, you ask, in a sense, the predecessor body of the parent joint, which sits again at the end of some branch that connects it to ground, but that branch is now one element shorter. So I basically reduced the problem by doing a little bit of math here to a shorter sub-branch. And then I repeat, and I basically, in every step, I make the problem simpler and simpler and simpler until I get to a point where it's trivial. And then I have a solution by putting these individual shorter sub-branches, in a sense, together. So that was algorithm 1, inward pass. The second algorithm is the outward pass. Where we typically, from the main program, start with root. And we will use the outward pass a lot more than we will use the inward pass, because often what we want as a main routine is to update everything in our kinematic tree, update the information in the entire system. So we start at root, and we call a function that somehow updates a particular body, actually more an entire subtree, but a particular body with some x set. When we call this for root, what should x set be? 0. 0 orientation, 0 or unity orientation, 0 position. We simply say for root, we already know, right? That's the origin of the coordinate system. In our implementation, we hence allow this function to be called without any arguments, and instead ask inside the body object itself, are you root? If yes, you set your own orientation to 0. So in a sense, you ignore what's in this variable or in this argument that is being passed xset. If you're not root, of course, you cannot do that. So you remember whatever was given to you, right? This is this part where we in our little game said, your orientation is 20 degrees, right? And when I called root, I never said your orientation is 0 degrees because I assumed that root knows that. And this is basically what we evaluate here. What's the next question that I have to ask myself if I'm doing an outward pass? That is something I would have to do, but I first have to ask myself a question. Yes? Yes. If you leave, because if you are, there's nothing left to do, right? You remembered the information given to you. You're up to date. There's nothing else you have to update. If no, then you, of course, have to go ahead and update all child joints. To the value x that you determined. And this update all child joints, of course, requires a corresponding routine in your joint objects where you update a joint to some value x set. And a joint doesn't have to remember anything. A joint just has to pass on the information. So it has to update its successor body. To what?
X plus delta x.
Yeah, x set plus delta x, which depends on whatever joint configuration we currently have, what joint angle. And we see, again, right, the information is stored in the bodies. Each body knows its own orientation, its own position. But the bodies don't do the math, right? The math is always done in the joints. So joints always basically goes from predecessor body to successor body, adding a little bit of math in between. And then the information is stored in the bodies, where you can now say the bodies are kind of stupid because all they do in both algorithms is simply, either retrieve information from a joint and pass it on, or get some information and store it internally. And then here, of course, when I update a successor body, what I mean with this is I'm calling this routine again, but now for a different body object, one level lower in my tree hierarchy. And in terms of a recursion, here I would say that I basically go ahead and treat the tree as smaller and smaller subtrees. Where I first call root, and root is the root of the entire tree. So my subtree is basically the entire tree. And then again, I or in the next iteration, I will call this a level lower and update a body, but at the same moment, that body is now the root of a smaller subtree, of a shorter subtree, and I can repeat this until at some point I'm a leaf, and at that point I am done. I have prepared code for this in MATLAB, which you will find in your in the examples or templates for that were posted today or will be posted tomorrow for exercise 4. Sorry, you had a question.
Yeah. In the invert method, we start with the leaf, right?
You can start with the leaf, but you can basically start with any body. If I just want to know arbitrary body, hey, what's your orientation of this particular body, I would do an inward pass, ask the body, and then that body would ask backwards until root. And the answer is being transferred back. Doesn't have to be a leaf, right? Could be anything in the tree. If I want to do the outward pass, I should always start with root because I want to make sure that really everything in my kinematic tree is being updated.
And like to iterate through the all bodies, we need to consider all of them, or just we are looking for one body in the invert method?
In the inward pass, you just want to know one particular body. And then, of course, you only basically sample that branch between that body and ground. And the other parts of the tree are not affected or not considered because they don't influence the position and orientation of that particular body, right? This is, if I want to know what's happening here on my upper arm, it doesn't make sense to look at my lower arm or to look at my right arm because none of these joints here are going to influence the position here.
But in outward method, you have to know all of them.
We want to update everything, right? So you can think about these two algorithms basically here. I'm interested in one particular body and just want to know what is this particular body doing. Here, I want to update everything. And this is why we will use this a lot more, because you can imagine in a simulation or in a kinematic simulation or animation, you would get at a certain time t, you would get a set of cues. Then you run this algorithm to update all the x's. Then you do a little bit of dynamics, and then you repeat with the new set of cues, right? And this is what we will see in a lot of our main files, that there's a lot of calls to this, right? Often in some loop.
For the outward pass, does it matter which child we traverse first?
No.
We have to first calculate the height of the child and then we update it.
No, it can be completely random. In any case, this is a depth-first algorithm, right? You basically keep calling children until you reach a leaf, the end of the tree. Then you're done, and then you back down into the tree a little bit and out to the next leaf and back into the tree. So you always go the entire depth of the tree first, compared to these breadth-first algorithms that would first do all children and then the children of the children and so on. Here we first want to go all the way to a leaf to the end. Yeah?
So just a question, in the inward pass, it's just considering one branch, not the whole
Yeah.
tree. So for instance, if you have a robot, it's just like from the right arm till the tip. So if you want to compute like the whole thing, you have to do multiple inward passes?
In theory, you would have to do an inward pass for every body in the tree, because from the perspective of the main routine, you don't know what is connected to what, right? So even if I have the simple tree, something like this, right? If I run an outward pass, it will go here, 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 and then I'm sure all bodies have been touched, right? If I just call an inward pass here, I, as a main program, then I know the position of this body, but I have no idea what other bodies have been processed, right? So if I would call the inward pass for this body from a main routine, I wouldn't know that this guy here already got information and potentially had been updated, right? So this is inward pass. We only use that if we want to know position and orientation of one particular body, somewhere there. Okay, there's another. Tian?
Yeah. In the inward pass,
Mhm.
no, let me rephrase that. In the outward pass, we already saved the position in the body. Then why do we need the inward pass? Because if the body is
You do one or the other. You wouldn't do both, right? If I did an outward pass, everything has been updated, and I don't have to do any of the inward passes. But it requires me to process the entire tree, right? But then let's say my Q changed, I have different joint angles, everything changed, and now I just want to know this guy, right? It would be much more efficient to just call the inward pass, because then I don't have to process these as well.
So when you change the position of a joint, would you do the outward pass or the inward pass?
We always will do the outward pass, because we then want to know basically everything in the system. Yeah. Sorry, yeah.
What would be application where I would only need the inward pass? Because that's also what I was wondering. Because if I can compute everything with outward, when would I need the inward pass?
It's just efficiency, right? That's if you have some situation where you really just need to know what's going on here, for whatever reason, right? The inward pass would be more efficient because it would ignore everything here.
Yeah, I understood that, but
We don't use it. So the short answer is the short answer is in our framework we are not using it. We're just using the outward pass. Yeah, I'm not even sure if it's implemented in the framework.
Is there a difference between computational efficiency of these algorithms? One is faster than another, or are they at the same speed?
I don't think there is a difference apart from the number of nodes visited, of course. No. Okay, that's some good discussion. The real question is, what the hell is x and what the hell is delta x and what is q? Right? For our little angle robot, that was just really an addition. But for a more complicated robot, or more complicated 3D joint, I should say, what is x, right? What is delta x? How do we compute it? What does it mean? And this basically brings us now to the next section here, where we will talk about motion across a joint. And if I consider a joint, it means I have some body that from the perspective, and that's important, right? Just the perspective of the joint is the predecessor, and some body that is the successor. And in between, there's a joint, and that joint generates some motion. And that motion depends on the joint variables q. I write them as a vector because there could be multiple motion primitives. And this is the perspective of the joint, right? If this sits in some kinematic chain, there's going to be another joint maybe back here. And from the perspective of that joint, this would be the predecessor. So a body can have both roles, right? The same body at some point can be a predecessor, at some point can be a successor. Now, in our framework, we said that we want to describe the motion of a body through a position of its center of gravity. So this here is the COG location, this point P, and a coordinate system with, let's say, an x-axis and a y-axis. And in a sense, right, from the perspective of a joint, that information is given. So I know the orientation of body P, given by some transformation matrix AIP, and I know the location of the center of gravity of this body, given by some vector RIP, where P stands for a point and a coordinate system at the same time. What I want to figure out as a joint, what is the orientation of the successor body, and what is the position of the successor body. And again, we will describe this through a point S, the center of gravity of the successor body, and some coordinate system S that gives us the orientation of the successor body. And so what I really want to figure out as a joint is the relative displacement, RPS, which depends on Q in some way, and the relative orientation, APS, which also depends on Q. Easy enough, but for the first time that I really wrote down what I mean when I say X, right? X is a transformation matrix and a position vector, and delta X is this relative position and then transformation between the two coordinate systems of successor and predecessor body, right? So we have given a displacement. That's my delta X, or part of my delta X, the vector RPS, which depends on the Q's that are assigned to this joint. And we have a rotation. That's the second part of the delta X. The rotation is a transformation matrix, APS, which also depends, or potentially depends, on the Q's. And with that, RIS is simply RIP plus this relative position. And AIS is simply AIP multiplied with APS, where APS may depend on Q. So this is what I mean with X and delta X. And now the details, of course, right? How do I compute this displacement? How do I compute this rotation, APS? That depends on the type of joint. And the type of joint is then ultimately what determines what my Q is. And I'm just going to give you some examples. And as a roboticist, the first joint, of course, I think of is a purely rotational joint that gives me a rotation between a predecessor and a successor, between P and S, a rotational joint. And here I would typically describe my joint with a single joint variable, right? There's just one motion primitive, a rotation about one axis, and that motion is described by some angle gamma. So Q, in this case, a scalar value would be this angle gamma. Another example could be a translational joint. Where the two bodies, predecessor P and successor S, glide against each other. There's a translational joint. And here I would, for example, describe the motion. Again, a single motion primitive. I would describe this with some delta x, some motion in this direction. And here, so my q would correspond to this delta x. Which of these two is more common in technical systems? And why? Okay, but why? Say that again, sorry.
It's easier to create motion with a motor.
Yeah, but why? Right, it's an interesting question. Why is it easier to have rotational motion than translational motion?
The way to create motion with electricity is by creating a changing electrical field.
But you could, I see your argument, but you could do this linearly the same, right? And the physics wouldn't change. Physics, rotation, translation doesn't make a difference.
It's a bit of an intuitive answer, but I think because the rotational joint is fixed at one point, but translation is along the line.
Yeah, it goes, I think, in the right direction.
Description?
What's that? I mean, there has to be some really fundamental thing why rotational motion is so much easier than translational motion.
Do you think it has something to do with movement of center of point and mass or something?
So I mean, this is not out of a book, but if you think about it, right? If I have a rotational joint, the area of contact is continuous, yet very, very short, right? It has the topology of a circle, which has a finite length. So if I do a ball bearing, I just need a number of balls, and they always spin in circles, and I'm done, right? The same with a motor. I just need a certain number of coils in a very limited space, and I'm done. If I have translation, I either need ball bearings or balls all the way along, right, and bearings all the way along. And then for linear actuator, you also need coils and magnets and along the entire way of travel, and I can never basically reuse them. Or with these with ball bearings for translational joints, what you typically do is that you recycle balls, right? So they roll along the surface, and there is some weird channel that brings them back to the front so they can start rolling again. And that makes them much more difficult to build. And I think that's the primary reason why we see a lot of this and not a lot of this. Two examples with just one motion primitive. I will not give you an example with two motion primitives, but I will immediately give you one with three motion primitives. And this is now a floating base, where my predecessor, in this case, would basically be equal to ground. And my successor would be the floating base. And because it's a virtual 3 degree of freedom joint, I have to allow, in the planar case, motion in x, motion in y, and some angle gamma. So this would be a virtual 3 degree of freedom joint. And here my generalized coordinates for this joint consists now of 3 variables. We have 3 motion primitives, delta x, delta y, and gamma. The last one that I want to discuss is a cylinder rolling. Oh, great cylinder. Good enough. Cylinder rolling on a surface. How many degrees of freedom does that joint have? right? That, I mean, it's not really a joint, but that constraint or that interaction of a rolling contact joint. What do you say? How many degrees of freedom? That's kind of the point, right? With this setup as I draw it here, I could make the case for there's no sliding. Then I have 1 degree of freedom, right? Rolling and translation are coupled. I could say I allow sliding. Then this thing could spin without moving forward or could move forward without spinning. Then I would have 2 degrees of freedom. If I think of this as a unilateral constraint and basically take the case where I lift it up and get it in 3D space, then sort of in this, in this situation, I would have 3 degrees of freedom, right? So there we have to be a little bit more specific what we mean. So here I say no sliding. And then I only have 1 degree of freedom, but I will get translation and rotation at the same time, right? I have some angle gamma with which this thing rotates, the cylinder, and I have some displacement delta x that describes how this cylinder moves laterally. And the important bit now is that the two are coupled. And I can only pick one of them as my joint angle. So I would say Q gamma equals Q, or yeah, maybe the other way around. But I pick one of them to be my Q. If gamma is Q, what is delta x? R, right? We need to know the radius of this thing. And by the way, even though my drawing does not indicate this, this is a circle. So we have here a cylinder, circle. And then, of course, delta x would be R times Q or minus R times Q, depending on how I define my directions. This would be sort of the holonomic view. And this is clearly a holonomic system, right? It can be integrated. In a lot of cases, it would make sense to model this as a non-holonomic system. Especially if you have cases where the cylinder may slide at some point, right, and then start rolling again. We use this a lot when we talk about legged robots that have spherical feet or circular feet, and the foot moves through the air, hits the ground, and then has a pure rolling constraint. And then it is often more convenient to not follow this holonomic description, because the holonomic description has a unique relationship between gamma and delta x. Whereas if I allow lifting up, right, I can break that relationship. I lift up, I change my gamma, I change my delta x, and then I'm in contact again. And then instead of redefining a new zero, it might make more sense to write this as a non-holonomic constraint, where I would then allow 2 Qs, 2 variables to describe my joint configuration, gamma and delta x. But I would only allow 1 velocity variable, which I would call gamma dot. Right? That's this idea behind how we treat joints when we think about them, or constraints when we think about them in a non-holonomic fashion. I have 2 position variables, 1 velocity variable, and then I have this translation between Q dot, which is basically gamma dot and delta x, and the u. And here we see that gamma dot is exactly u, and delta x dot, of course, is r times u. Not necessary. Oops. not strictly necessary, but sometimes more convenient if you don't want sort of this fixed relationship between position and orientation, but you just want that relationship locally as it corresponds to rolling. So far, so good? No?
If the circle is totally symmetric, what is the meaning of the angle here?
Good question. We'll talk about this in a second. Yeah? Any other questions? Right? Or what is the meaning of 0 to phrase it a little bit broader? What is the meaning of Q equals 0? Yeah? How can we make sure that when we say Q is 0, everyone means the same thing? Other question?
We can have delta x without gamma if we have slipping or
If we have sliding, yeah.
or sliding, or
If you lift up, yeah.
But we can't display it with the non-nomic, I think. What would you do there?
We will talk about contact later, because you have to model this as different phases, right? You have a phase with sliding, and then you basically have a collision, and then you have a rigid connection. So your constraints change, and that basically is similar to these unilateral constraints or changing constraints. We'll get to this, but there it makes then sense to consider the formulation on the right, because I don't have a global connection anymore between position and gamma. Right? At every moment, if I don't slide, I have a connection through the velocities, but sort of globally, if I allow at some point that you lift up, you can rotate and then put your foot or your cylinder back down, and that global relationship has been broken. Right? That's why I introduce it, but something that we will get to. Good. I introduce you another problem, and that is actually very, very simple to explain. Here I have a very, very simple rotational joint, and I depicted my predecessor and my successor for two joint angles Q1 and Q2. And I see APS of these two joint angles, and I see RPS of these two joint angles. And sort of the unpleasant thing that I want to point to is that I have a purely rotational joint, but it is creating a displacement. Right? And you can see that this will make the math tricky. That even a purely rotational joint creates some spatial displacement. We will figure out how to do this, but that's not particularly pretty. How can we fix that? Does someone have an idea? What could we do?
So can you repeat the problem?
Orange arrow is the problem, right? I have a purely rotational joint. All I want is to say I have pure rotation, which should be super simple, but I get a displacement, right?
Is it straight displacement?
This would be an arc, right? Between the two, it's straight, but in between, you're right, this would be moving on an arc. So it's not trivial, right? And somehow depends, this displacement depends on Q. What could we do to simplify this problem?
Maybe we can translate the coordinate system to the point of joint.
Yeah, that's exactly the idea. And we will use joint coordinate systems. And instead of just translating, we will add two joint coordinate systems that we will call dp in the predecessor and ds in the successor. And they are defined relative to the predecessor coordinate system and the successor, and the successor S respectively. And I will introduce now a convenient convention for Q equals 0. What would be a convenient convention here? These two coordinate systems are aligned. So dp and ds are basically in the same orientation and at the same position when q equals 0. That's now my definition of q equals 0. That kind of corresponds to this idea of having no displacement and having no rotation. So, in the situation that I had above, here's my predecessor. With its center of gravity and body coordinate system here. This is clearly not a homogeneous body if the center of gravity is there. And now I add my dp system, and I add it right where I want my rotational joint to be. So this would be my dp system. And this would be my successor, S, somewhere here. And I would add a ds system, and I will draw the ds system at exactly the same location as the dp system, because I'm here depicting the situation where q equals 0. Important difference, right? The gray coordinate system is fixed to the predecessor. The orange coordinate system is fixed to the successor. So if I draw the same system for a different joint angle q, and if I draw the predecessor at the same location, the dp system will still be at exactly the same location. But now the successor has rotated. And I still see sort of this rotation and translation of my point S. Right? I still have this motion. Of course, that's physically there. But if I now draw my ds coordinate system, it will show up somewhere like this. And I see that the motion between dp and ds is much, much easier. Right? Here, I now have a pure rotation. And I get that, because in a sense, as you said, I moved the coordinate system to where the joint is, or we just added coordinate systems where the joint is. So these are joint coordinate systems, fixed, one in the predecessor, one in the successor. Advantages: it will get easier to compute the motion, right? The motion of the joint is easier to describe. A rotational joint will simply have a pure rotation. pure rotation, of course, between these two joint coordinate systems, so between dp and ds. We also now have a clear definition what q equals 0 means. And I hope that answers, who did ask the question? That answers your question, right? So we would just have to look, where's the predecessor coordinate system, where's the successor coordinate system, and for q equals 0, they will be aligned. And then there is a third advantage, which is almost the most important one, and that's something that we don't see in 2D, but in 3D. If you have a 3D system, right, like looking at my arm, I have a rotational joint here with this joint axis, and I have a rotational joint here with this joint axis. Right? So they're orthogonal to each other. Now I could go ahead and say, okay, I now need to define a joint about the x-axis and a joint about the y-axis and a joint about the z-axis. Hold on, right? Do I also need a joint about the halfway between y and z-axis? Do I need a joint, right? That doesn't work. I cannot define a joint type, a specific joint type for every possible axis. But I now can go ahead and work with these joint coordinate systems by simply saying, okay, first of all, I always define the z-axis as my axis of rotation. This is a de facto standard, right? You could pick anything, but if you look in the literature, they always use the z-axis. Why? Because in planar systems, that would be the axis of rotation, right? So translation x, translation y, rotation z. I put it here for the elbow joint, right? And my coordinates here are maybe like this, right? So for the elbow joint, right, this is my predecessor body. This would be the joint. There's no rotation, right? Just the pure translation, and then I get this rotation. But now if I think about between here and here, I want the joint axis to be this way, and my body coordinate system would still look like this, right? I still move like this, but I can now go ahead and define a transformation, some matrix APDP, that transforms this such that my dp system has the z-axis aligned with the axis of rotation. And then I do the same here, and I can basically, with one rotational joint, I can realize every possible rotation axis. With one translational joint, I can realize any possible translation, right? I only need a translation in the x direction. If I have something that translates in the y direction, I would go ahead and rotate my joint coordinate system such that the y-axis, the x-axis of the joint points in the y-axis of this body. Last time, I promise. And you can imagine, right? Since we can have infinitely many joint axis direction, this is a necessity. So last point, but probably most important, the joint axis is flexible. For now, this makes our problem more complicated, because now I have to think about more coordinate systems. So here's my predecessor, P, and somewhere within this predecessor, I have a joint coordinate system, dp, and also, of course, an origin of this coordinate system. So there's both a coordinate system dp and a point dp. And I somehow have to store as information, and this is information that should be stored in the joint, right? I'm drawing things in a body, but these are things that actually concern the joint and should be stored in the joint. I have a vector rp dp, and I have some transformation AP dp. I then have motion in the joint, and in the general case, the motion in the joint could be translational with some vector rdpds, and rotational matrix A dp ds. Right? And for most of the joints that we will see, one of these two is going to be 0, right? If you have a purely rotational joint, rdpds is 0. If you have a gimbal joint, rdpds is 0. If you have a ball and socket joint, rdpds is 0. If you have a purely translational joint, adpds is going to be the identity. So this is where we gain a little bit that for many joints, these expressions are actually going to be simple. And they connect to our successor body, S, coordinate system, point. And within the successor body, we have now also defined a joint coordinate system, ds, with the corresponding origin that we also call ds. And again, we have to record this through some vector rs ds and through some transformation as ds. As a side note that will become important in just a second, they point in opposite directions, right? If I think about this joint going from left to right, from predecessor to successor, RPDP points in joint direction, RSDS points against joint direction. That's one note. The second note, everything that is drawn in gray is body fixed, right? Joint and center of mass and joint coordinate system are all part of the same rigid body. So if I express these quantities in body fixed coordinates, they will be constant. That's also an important advantage. And with this, I now have a slightly more complex way to compute my overall displacement, RPS, where RPS is now the vector from P to the dp system, or the origin of the dp system, plus the vector across the actual joint. That is the only thing that depends somehow on Q. And then here with a minus sign, because it's defined in the opposite direction, the vector from S to ds. And the relative orientation, APS, between predecessor and successor, that is given as APDP, so relative orientation between predecessor and predecessor joint coordinate system, ADPDS, that one depends on Q. And then here I have to multiply ASDS with a transpose, right? Where the transpose is basically the counterpart to the minus sign, because ds is defined in terms of s and not the other way around. Quick questions?
Question?
Yeah?
So it's a little silly question, but what constrains us from like not choosing the dp there at the start? Like what makes us choose the p where we chose it?
In this case, this is, I mean, very generic, right? And as soon as I have a translation and the rotation, the question where to place these actually becomes quite tricky. We will get to an exercise where we'll ask the question, where do you place these systems when you have a rolling contact, right? Where the actual rolling contact happens down here, right? This is where contact happens. This is where you would think the joint is, but this is not where we would place the joint coordinate system. So if you have a mix of translation and rotation, it gets tricky. But for pure rotation, it's obvious, right? Place your joint coordinate system as the joint axis. For pure translation, place your coordinate system such that it aligns with the translation direction, where the goal is, of course, that you choose these coordinate systems such that these quantities become as simple as possible, ideally 0, right? Here's a cleaner drawing, right? You have this in your templates as well. And so far, we've wrote everything as, what did I do? We've wrote everything as vectors. What happens if we write things in terms of coordinates? So the given quantities, right, to reiterate, you know the position of the predecessor, right? RIP is a given quantity, which is interesting, right? Why do I always know the position of the predecessor? Why can I assume that I know the position of the predecessor? Because of the recursion, right? If I don't know the position of the predecessor, I move one joint up, and then maybe there I know the position of the predecessor. And if not, I move one joint up and one joint up. And at some point, I'm at root, and then I most certainly know the position of the predecessor. And once I know the position of the predecessor, I can do the math that we will derive here to know the position of the successor. And then I can move to the next joint, where the current successor is then going to be the predecessor, and then I'm sure I know it.
Can we just not say the predecessor is the ground?
No, because this can happen anywhere in the tree, right? And of course, you have to back up until you're at ground, but then you can compute the position of the successor, right? This is when we then start doing the outward pass or move back through our inward pass and add the delta x's. And then at every time what the joint does, right? The joint always did x plus delta x, where this is x and this is delta x. So we know RIP. We also know RP dp. That is by design, because someone, if we do a simulation, someone has to tell us where is the joint located within the body. We know R dp ds, or we can compute it somehow from Q, right? We know the joint angle, so we can compute that. And we know RS ds. Again, a question of design. Where is the joint located in the successor? And what we want to find is RIS, the position of the successor. And the first question that I want to raise here is, in which coordinate system do I express each of these quantities? In which coordinates do I represent RIP? There's two options, right? E or P. We're going to do P. Why? Yeah, we decided at some point to express all quantities in body fixed coordinates, right? When we talked about motions of rigid bodies, we said we want to do everything in body coordinates and p coordinates. Why? Right? Wouldn't it be easier to do everything in inertial coordinates? Why did we do transport theorem and moving coordinate systems and all that crap, right? Why in P? Yeah, that's the reason, because then the inertia matrix is constant, relative positions are constant. A lot of stuff has to be defined once and then doesn't change. Everything that's body fixed is constant. That's why we do P. RP dp in which coordinates?
Also P?
In P. For exactly that same reason, this should never change. And then, of course, RS ds in S coordinates. RIS, our result. What coordinates?
P? Or no, inertial.
Okay, I think now we have it all covered. I can just pick an answer. No, in S, of course, because now again we want to express the position of the successor, which is a body, in its own coordinate system. So if we talk about the motion of S, we want to express it in S. If we talk about the motion of P, we want to express it in P. What do I put here? dP or ds? Seems like doesn't matter, right? I'll pick dP. I'll talk in a second about what's the difference. What happens if I consider it to be in ds coordinates? What happens if I consider it to be in dP coordinates? And now with this, I can go ahead and compose my overall calculation of x plus delta x. So for rotations, this means AIS is the orientation of the predecessor body times the relative orientation of the joint coordinate system times the rotation across the joint times the rotation between the successor and the joint coordinate system of the successor, where I need the transpose, right? Because that is defined in the other direction. RIS, I want that in S coordinates. And I'll leave a little bit of space because I know that there's a bunch of vectors that are given in P coordinates. RIP is given in P coordinates. RP dP is given in P coordinates. And then I could use AP dP to transform my vector, my joint displacement, so R dP ds from dP coordinates into P coordinates. So all of this is in P coordinates and needs to be multiplied with APS transpose to get it into S coordinates. And then we have sort of as an only exception this vector RS ds, which is already given in S coordinates. And that one has a minus sign. So this is everything in coordinates, where I have to think about the different coordinate systems that I'm carrying around. Now, I want to give you an example of a simple joint motion. AdP/ds is, and I'm going to do this as something two-dimensional just to keep it simple. This is my AdP/ds. Rotation by 90 degrees, which takes the dP system and rotates it into a ds system that looks like this, right? So this would be x and y, or one axis and two axes, however you want to call them. Pure rotation. And then I have a displacement that I will write as 1, 0 in two cases. So the numerical values, the coordinates are the same in both cases. But in the first case, I say that this is given in dP coordinates. And in the second case, the displacement is given in ds coordinates. And I'm basically curious, what is the difference? Right? What do I get when I define my displacement dP ds in dP coordinates? What do I get when I define it in ds coordinates? Well, let's give it a try. So if this is my dP system, where and how would I have to draw the DS system in case A? Right, that's my translation, my translation, my rotation. Rotation is the same in both cases. Translation has the same numerical values, but given in different coordinate systems. Where do I have to draw DS here? Yeah, 1 unit to the right and rotate it down. So if I say this is 1 unit to the right, this would be my DS system in case A. Right, so X and Y. Where would I have to draw it in case B? Why to the left?
Because we're in DS coordinates and we would then go the X, oh no, sorry, from left and up. No, only up, sorry. No, I get it.
The correct answer is down. I think you mean the right thing, but the idea, of course, is right now this is given in DS coordinates, and we move 1 in the X direction, and the X direction points down. And we would end up here. I'm sure that's what you meant. No?
I mean, yeah, the idea, yes. But isn't the X direction downwards? Oh, because of the...
This is X, this is Y, right, of the DS system. So they flip, and here I should have noted this. This is X and this is Y, or 1 and 2 axes, as you want to call them. So different result. How would you describe the difference?
The order that you rotate and then translate.
Yeah. So here I first translate 1 and then rotate 2. Here I first rotate 1 and then translate 2. So here translation, then rotation. Here rotation, then translation. We've seen this at some point in our first exercise, where we talked about rotational joints in Simscape. And there we had these coordinate systems. Do you remember how they were called? Base and follower. Right? And when we switched base and follower, we would basically switch. Well, there it actually would be more, because we would switch the order and the direction. It's very, very closely related to this idea of base and follower, where for us dp is the base and ds would be the follower coordinate system. And there's no true or false here, right? Which of these is better? It's pure convention. And we, for this class, we decided to express our joint displacement in dp coordinates, which corresponds to this definition we described: rotations, translations first and rotation second. But you can easily find another implementation or another book where they define it in ds coordinates, because they want to do rotations first and translation second. All right, questions? Quick example. If I have a pure rotational joint, how does ADP ds and RDP ds of Q look like for a rotational joint? where we would pick Q to be equal to the joint angle gamma. Right, so we would get an AdP ds of gamma and an RdP ds of gamma. And one would be a 3x3 matrix, and the other would be a 3 vector. How do they look like? Maybe we start with RdPDS. 0. That's the whole point of this exercise, right? This is why we introduced these. Now we have a pure rotational joint, and it's described by pure rotation with 0 translations. How does AdPDS look like? What's on the diagonal? Yeah, Jan?
It's a rotation matrix around which the axis you choose.
Okay, and I will choose this one, the z-axis, because that's basically the de facto standard. And then I have a very simple rotation matrix with cosines on the diagonal, sines on the off-diagonal, and that's it, right? And now I have my rotational joint. And I could have picked any other axis, and it would be equally correct. But then when I put together my model, I would just have to make sure that instead of aligning the z-axis with my rotation axis, I would then have to align the x or the y-axis or whatever I picked with my rotation axis of the joint. And that means this covers all rotational joints, right? If at some point someone asks you, how does this joint look like for rotation about the x-axis, you just smile at me and say like this. Okay? Deal? Questions? No? I'm almost surprised. Okay. I want to move towards velocities, and let's see how far we get. But on some level, I want to restate positions in a slightly different form. I mean, we've written down the equations already. Yeah? Yes?
Gamma is defined from dp to ds.
Yeah.
Okay.
Yeah, so positive, if I would draw it, I would say if this is dp and this is ds, then this would be gamma, right? ds dp, right? The same way we would define a positive x sort of in the direction of our dp system.
The reason why it is same for all the joints is that we always keep rotation on the z-axis, right?
Yeah, we always can pick our dp, our APDP, right? We can change that and then align the rotation axis, the z-axis, with whatever joint axis I currently have. This one or that one or that one. Sorry, that one.
Basically, if you have a spherical kind of joint, we simplify into 3 different relevant joints.
If you do a ball and socket joint, you would do it, I mean, there's different ways of doing it, but I would go ahead and use some Cardan angles or Euler angle convention, right, depending on the applications. Or if you think, for example, about a hip joint, right, what are the ranges of joints that you could get, right? There's a typical ball and socket joint, and then you pick a representation where you make sure that you don't see gimbal lock. Yeah, because that's kind of the thing that you want to avoid. Otherwise, you would have to go to a quaternion representation or something like that. Okay, positions, and I'm just restating what we had before, but instead of doing this in one step, I want to do it in in 3 smaller steps, where sort of step number 1 would be to say RIDP is RIP plus RPDP, where all these quantities on the right-hand side are expressed in p coordinates. And on the left-hand side, I want something in dp coordinates, sort of as an intermediate result. So I would have APDP transposed in between these two. And this would be sort of step 1. And then based on that, I could now continue and say RP, of course, the purple result that we just got, RIDP, given in dp coordinates, plus the translation across the joint, RDPDS, which is given in dp coordinates, will give me RIDS, the position of the successor coordinate system. And sort of sticking with this notation that I want this in ds coordinates, I would have to make sure here to pre-multiply with ADP ds transposed. And then I can repeat that process again and now take the position of my successor coordinate system in ds coordinates and subtract now minus sign r s ds as a vector. And that is already given in s coordinates, so I can make my parenthesis a little bit shorter in this case and only multiply the first vector with this matrix as ds, now without the transpose, kind of reflecting this minus sign. And now that would give me the position of my successor in s coordinates. Right? And if you insert these 3 equations into each other, you will end up with the equation that we have here. So nothing new. I just wanted to prepare this, that we can do 3 simpler steps, preparing you for velocities. And the 3 steps look almost the same. There is a small difference that this guy here is defined sort of backwards. So there's no transpose, there's a minus sign, and here we don't need a transformation matrix. What is the bigger difference between the 3 steps? This and this is fixed. This and this is fixed. Everything in red depends on q. And that will be important on Tuesday when we start talking about velocities, because then, of course, the derivatives of this will depend on q dot, on the joint velocity, whereas the derivatives on this will only depend on the transport vector. Okay, I'll stop here. Good time to stop. Thanks for being so interactive today. It's a lot of fun teaching this class this term, so thanks to you. Have a good weekend.